We'll illustrate next the tracking of a moving point, namely the estimation process for a point whose motion is nearly constant velocity along the x-axis, that's motion in one dimension only, and the state vector for this consists of position and velocity xx dot, and they will be estimated by x hat and x dot hat respectively. And we'll have a covariance matrix of the state, that xx dot, a 2x2 matrix, which indicates the uncertainty region around the estimated state. And knowing this, we will know the region around that state where the true value, the region around the state estimate where the true state lies with high probability. We start, say, at time k, where we have an estimate for position x hat sub k, position estimate, and the velocity estimate x dot hat sub k, and this circle symbolically represents the covariance, which means the true state is with high probability somewhere in this circle. We'll see later a more detailed description of such regions of uncertainty. The next thing is we predict the position from time k to time k plus 1. In the absence of any other information about the velocity, the predicted velocity at the next time will be the same as the current one. So you can see this value coincides x k plus 1 minus dot hat with the previous estimate. And the position, predicted position, is x hat k plus 1 minus. So this is obtained obviously by knowing the time interval for the prediction. And there will be an uncertainty, and this uncertainty will typically be larger than the uncertainty at time k for the following reason. We don't know the motion perfectly. Therefore, the predicted covariance, again described symbolically by a circle in this case, is pk plus 1 minus a larger circle. Now what we get is a measurement, zk plus 1, a position measurement only. Once we get this position measurement, if you notice, what we have here is this position measurement is behind the predicted position. So the way the update is done, and right now we see it only qualitatively, is the new estimated position will be x hat k plus 1, a little bit behind the predicted value because we use the correction from this measurement, and the velocity will be also corrected from x dot hat k plus 1 minus to an x dot hat k plus 1, a little bit lower velocity. So what we do is essentially modify both the position and the velocity from the predicted to the updated values by using this information. And here is the measurement. Zk plus 1 is xk plus 1 plus the measurement noise at k plus 1. And the new position estimate will be, as indicated before from the figure, between the observed and the predicted values. So the x hat k plus 1 minus will be lowered to an x hat k plus 1, which is somewhat larger than zk plus 1. So this is the compromise, that weighted linear combination between the predicted value and the observed value. And that's because the measurement minus the predicted value, this quantity is negative. So we will be also at the same time correcting the velocity. We update the velocity, come with the new updated value for it, slightly lower than the predicted value. Now, the covariance obviously has a detailed calculation with some matrix expressions we'll see later. But what is of interest now, again, to get a qualitative feel for the way in which we extract information about both position and velocity using, in this case, only position observations, is the following. Under stationarity and state observability conditions, the variance of the estimates will converge to a steady state value, as shown in this figure, where the prediction and updated variances are shown. Start with the initial variance, P0. Now it's illustrated in a scalar manner. You can consider it might be the trace of the covariance matrix. It gets larger, increased to P1 minus. That's a prediction from 0 to 1. It is updated with the measurement at 1. Then it becomes smaller. Then we get to P1, which is predicted to time 2, get to P2 minus, updated to P2, and so on until it turns out there are mathematical conditions we'll see later that it goes to a steady state. So there is one constant value for the updated covariance, another constant value for the what's called one-step prediction covariances. Now, if you look at the Kalman filter, which has a weighted combination between the predicted state and the updated state, it is really the stochastic counterpart of the deterministic state observer, the so-called Lumberger observer for linear deterministic systems. When the covariance is in steady state, the filter gain, the Kalman filter gain, becomes a constant. Now, such filters have been known for quite a few years, from the 1950s as a matter of fact, when they are for so-called nearly constant velocity motion models, are known as alpha-beta filters. Now, the Wiener filter is really the frequency domain counterpart of the steady-state Kalman filter. But obviously the Kalman filter does not require stationarity, but under stationarity conditions it will coincide with the Wiener filter. Now, the sampling interval, time between successive measurements, does not have to be constant in the Kalman filter. That's because it does not require stationarity. We can also have totally non-stationary disturbances like measurement noise with time-varying intensity can be easily accommodated by the Kalman filter. We'll take a look now at another example, that's vehicle collision avoidance. Again, we'll estimate the distance and the rate of change of the distance between two vehicles in this case. So the distance and the speed, relative speed between two vehicles. We'll look in detail now at an algorithm that will estimate the distance, which is range, and the relative speed, which is the range rate, based on imperfect, namely noisy measurements of the distance between them. This algorithm is really a simplified version of the Kalman filter. It is the so-called alpha-beta filter, which we'll see now. And at a later time in the course, we are going to provide the derivation how the alpha-beta filter is really a particular case of a Kalman filter. It can also be viewed as a state observer, which, based on observations of one state component, will reconstruct, will estimate the entire state vector. So really, it is a connection between deterministic linear system theory and stochastic systems. You can see it in this way. We define the state vector consisting of range and range rate. The vector is x, first component x1, second component x2. Now, if we assume a constant speed or constant range rate, the state equation is for discrete time with a constant sampling period t, x at time k is this matrix times x at time k minus 1, which is f x k minus 1. F is the transition matrix, and this really represents a double integration. The velocity r dot is the same as the previous one in this model, and the position at time k is the position at k minus 1 plus t multiplied the velocity at k minus 1. The measurement will be the first component of x, so y is x1, that's the range. This is 1, 0 row vector multiplying the column vector x. So that's hx, and here is the measurement matrix H. We are using notation that will be common later in carbon filters. However, up to now we had a totally idealized model. We got to get closer to real engineering systems. The measurement in the real world is a corrupted version of the range. So it is not hx, but hx plus some w. And w is the range measurement error. So Ry now is an imperfect position or range measurement. Similarly, the assumption that there is an absolutely constant velocity or range rate between the two vehicles is not realistic. So what we have to do is introduce another term in the equation, namely a relative acceleration, which multiplied by time changes the relative velocity, multiplied by t squared over 2 will give the position displacement due to the acceleration. However, we don't know u. So what we have is really a model in which there is a u that we don't know. So the question is, can we have a filter and its performance analyzed in view of the fact that we don't know u? So this is what we are going to do next, is evaluate the effect of these modeling errors. Okay, what is the estimator? Clearly we have both measurement errors and motion modeling errors. We shall calculate the estimate x hat k, that's a vector, consisting again of the range and the range rate, via the following algorithm, which is a simplified form of the Kalman filter, and that's exactly the alpha-beta filter discussed later in these chapters. X hat k is x bar k, and this would be the notation we are using now for the prediction 2 times k from time k minus 1, plus some gain matrix, and the alpha and beta will show up inside W in a moment, times the residual. This is the actual observation y at time k, and y bar at k is the predicted value of that observation before we get it, which means using the information from the previous time. Now here's the expression of x bar k, the predicted state at time k from k minus 1, or 2k from k minus 1. X bar k is fx hat k minus 1. Because we don't know the term u, we assume it in this prediction as equal to 0. And this is going to be given by this, that's the f matrix, the transition matrix, times x hat k minus 1. Now the x hat is written out explicitly as an r hat and r dot hat components. And here you have clearly the fact that the predicted velocity at the next time is the previously estimated velocity or range rate, and the predicted range is the previous range plus sampling interval multiplied by the value of the estimated range rate at the previous time. So this is the predicted state. Now we need the predicted measurement. Again, we don't know what's the W, the measurement noise, so we take it 0. So y bar k is hx bar k, and this becomes just the predicted position because h is the row vector 1, 0. So this term just picks up the first element of this two-dimensional vector. Now, the residual. The difference between the measurement, which is the observed range, and its predicted value, that's y minus y bar, or y minus hx bar, is what we call the residual, and it will be multiplied or weighted by the so-called filter gain W, which is written in this fashion as alpha and beta over t. Both alpha and beta are dimensionless quantities, because alpha will convert position into position, beta over t has 1 over time, converts position into velocity. So this residual will be multiplied by the gain W, will correct or update the predicted state to obtain the new estimate. So our filter really can be seen as a predictor-corrector algorithm. You predict, you correct. After you get a measurement, again you predict, and again you correct or update. Okay, these constants, alpha and beta, both are dimensionless, as indicated before, are such that alpha is between 0 and 1, and beta is between 0 and 2. And these are the two quantities which define the alpha-beta filter. Now, let's look in detail at what happens with the components of the state vector in the process of estimation. Here is the updated range at time k. This is the previous range plus t times the previous range rate. That's, these first two terms are the predicted range, plus alpha times the residual. The new updated range rate is the previous updated range rate plus beta over time times the residual. And now you can see that this is position, beta is dimensionless, this is time, so this beta over t converts a position into a velocity. It's very important that the dimensions are, the physical dimensions of these quantities are consistent now. Okay, so we can now provide an intuitive interpretation of the last equation as follows. If the predicted range is larger than the measured one, the residual will be negative. And we apply a negative correction, remember alpha is positive, with the gained alpha between 0 and 1 to obtain the new estimated range. So we do a compromise between the predicted range and the observed range to come up with the new updated range. And this is very completely consistent with the original picture where it was shown in that one-dimensional motion. That is the way a negative residual will correct the position from predicted to updated is as a smaller value, namely we make a negative correction. Now, if the predicted range is smaller than the measured one, residual is positive, then we make a positive correction. Similarly, the range rate is corrected downward. Remember, beta is between 0 and 2, so the gain beta over t isn't positive. Is corrected downward for a negative residual and upward for a positive one. And again, important to remember that the residual has dimension of length, and multiplied by beta over t, it becomes length over time, namely velocity. Now, up to this point, the impact of u has not been quantified. Now we got to evaluate, analyze exactly what will be the impact of that unknown, possible unknown acceleration. If we assume in our error analysis, we'll do a deterministic error analysis, that there is a constant acceleration or deceleration, u, then our equation is given by xk is fxk minus 1 plus gu, where u is now a constant, g is the t-square over 2, its impact into position, and t maps it into its impact into the velocity. So this is now u. So what we want is to take the filter equations and evaluate the error due to the fact that there is a u there. We don't know it, so we'd like effectively to bound that error. Okay, assuming the measurements are given by our position equation, and now we are neglecting the measurement errors, we'll evaluate the effect of the acceleration on the errors in the range and the range rate estimates only. So what we are going to do is use the fact that this is a linear system subject to two types of error. There's a measurement error and there is a motion error. And because this is a linear system, we can use superposition, which means we can take separately and evaluate the effects of those errors. So the error is defined as the difference between the actual value and the estimate. X tilde will be the common notation for error. Tilde is x minus x hat, and this comes from the fact that x tilde plus x hat equals to the true value x. Now, the dynamic equation obeyed by the error x tilde is a state equation with system matrix. We subtract the x and the x hat, the two equations, one is the dynamic, one is the filter, and we end up with a linear equation. X tilde is f tilde x tilde at the previous time plus g tilde u. With a little bit of algebra, f tilde turns out to be I minus WHF. Here are the elements of this matrix. You can see the alpha and the beta, how they come in. And there is a gain G tilde on this effect of the unknown input, that unknown acceleration on the state estimation error. And again, is given by terms containing alpha and beta and obviously t. Now, it can be shown that the inequalities indicated earlier for alpha, namely between 0 and 1, beta between 0 and 2, guarantee that the matrix F tilde, which governs the evolution, the dynamics of the error, is a stable matrix, namely it has eigenvalues inside the unit circle. This is a discrete time where the eigenvalues of the transition matrix have to be in the unit circle, and this is the counterpart of the continuous time version, where for a linear system the eigenvalues of the system matrix have to be in the left half plane. Now, what we have is a constant disturbance u. X tilde will converge to a steady state value. Because of the stability, we can solve the equation. We know there is a single asymptotic solution, and the solution, this solution is X tilde steady state is I minus F tilde inverse G tilde U, and this is an expression, a two-dimensional vector multiplying U. Now, the question is numbers. In a real engineering system, we've got to come up with numerical results. If you assume U as 5 meters per second square, and this is approximately the limit of the ability of a vehicle to decelerate is half a g. Typically, they don't accelerate anything close to that, at least not linearly. Sampling interval 0.1 second. The gains for the filter, which I cannot justify at this point, but we'll see a systematic way how you can design a filter, how you can come up with gains based on the properties of the system. Alpha is 0.75, beta is 0.5. We obtain the steady state range error as 0.4 meters, a little bit over a foot, and the range rate as 0.5 meters per second. So we have now a quantitative evaluation of what the impact of the quantity that was not accounted for in the filter, because we don't know it. What is a bound on its error, assuming this is the maximum vehicle, say, deceleration capability. Now, it is interesting to connect this discrete time filter, which is a dynamic system, with what we know as transfer functions. And each transfer function has a frequency response. So what we are going to do is obtain the transfer function, and before we go through the algebra, we can see that this alpha beta filter is indeed a low pass filter. And for those numbers, roughly up to about 2-3 hertz, you have here the cutoff frequency, and it's good to understand that we have a certain bandwidth, which we'll obtain in a moment. Now, Again, a little bit of algebra. The following Z domain, the Z transform domain transfer function from the input U to the error X tilde can be obtained. So H tilde now is a transfer function to the output is X tilde, function of Z, that's a Z transform over U of Z. And this is Zi minus F tilde inverse G tilde. This is the standard expression of the transfer function in the Z domain based on a difference equation. And we can put in these numbers and we find the transfer function given by this expression in the Z domain. We can look at the poles of this. It has two poles. They have magnitude half. They are within the unit circle, so this confirms the stability. And we've shown already the plot of the magnitude of this transfer function for a range of frequencies between 0 and 1 over 2t. The upper limit is the point for which the Nyquist frequency is really the sampling frequency. So we go up to 1 over t. It is a low-pass filter and has an approximate bandwidth based on the half power point of 2 Hz. Okay, with this introduction, we'd like to provide a quick description of what the main part of the course will consist of. We want to study the fundamentals of state estimation theory and the tools for the design of state-of-the-art algorithms. That's an engineer's #1 job. In this case, the application will be target tracking and navigation. We'll cover the basic concepts and estimation techniques for static and dynamic systems. This is really parameter estimation for static systems, state estimation for dynamic systems. We'll look at linear and non-linear situations as well as adaptive estimation. The reason we need adaptive estimation is because our knowledge about models can evolve, or the models, mathematical models obeyed by systems, can change with time. So we really have major non-stationarities, and this is the area where recent advances allowed us to develop very efficient techniques. It's a typical electrical systems engineering program. It really, this whole information extraction area that we are going to cover is what can be called also the prerequisite for information fusion. We'll emphasize statistical tools that can be used for interpretation of the output from stochastic systems. It is important to understand that when you have stochastic systems which every time behave in a somewhat different manner because there is an inherent randomness there, we've got to interpret those results. We'll illustrate estimation algorithms or kinematic motion models because they reveal most of the major issues and subtleties encountered in estimation. We'll provide guidelines for the design of tracking or state estimation filters, namely selection of the filter design parameters, but more, one level above it, selection of the type of filter which will be in this case either non-adaptive, namely based on a single model, versus adaptive, based on multiple models. And in the real world, many systems do not obey a single model, but for a while they behave according to one model, then according to another model, then back to the first model, then on to possibly a third model, and so on. There is a software Dynaist which is available for download, as the text indicates, from our website, and also a step-by-step demonstration how to use Dynaist is provided in the text. Now, what do we need in order to follow the material for estimation. Number one is linear algebra. That's really state space analysis, which we'll cover in the next section, and we'll also discuss some useful results for linear systems. Controllability and observability play a major role. We'll use matrix notation pretty much every time a quantity should be considered a matrix unless otherwise stated. Then we'll go on to review tools from probability theory and random processes. And after which we'll discuss statistical hypothesis testing. That's decisions. How to make decisions between different possibilities in the presence of uncertain data. And we have some tables for chi-square and Gaussian distributions that we'll cover, and we'll pay attention to the concept of statistical significance, which probably engineering literature doesn't cover it very much.